out who's really at risk. Okay, so we've got a much better tool for finding the clues. Awesome. But that just reveals the next big problem. What happens when the labels we're using, the phenotypes, aren't perfect? What if we need to let the data speak for itself?
I mean, just think about it for a second. Labeling someone as either has the disease or doesn't have the disease is, well, it's pretty crude, right? Biology is almost always a spectrum. Plus, how are you ever going to get a doctor to sit down and create detailed labels for 1 million people? You can't. It's a massive bottleneck.
And this is where AI phenotyping just completely changes the game. Instead of those clunky yes or no labels, we can just feed the AI the raw data itself, like here's a detailed scan of an optic nerve or a lung function curve. The model then learns all the important patterns on its own and spits out this super precise, scalable score. So now you get a much richer picture, and you can do it automatically for millions of people. Problem solved.
But okay, what if we could take it even one step further? This is where a technique called Reglet comes in, and it uses something called unsupervised learning. This is wild. It means you don't give the AI any labels, not a single one. You just hand it the raw data, say a bunch of lung function tests, and it just figures it out. It finds the important patterns all by itself. It's literally like giving the AI a flashlight and telling it, go explore this dark room and tell us what you find.
Okay, so we've taught our AI to look at one type of data with superhuman precision. That's cool, but think about how we understand the world. We combine our senses, right? What if we could teach an AI to do the same?
Right? So looking at just one data type, that's called unimodal. It's like trying to understand an orchestra by only listening to the violins. You get part of the story, but you're missing the whole symphony. The new approach, called multimodal, is about hearing everything at once. And a new method, Emrigal, does exactly that. It listens to all the instruments at the same time to find harmonies, these connections that are completely invisible when you're just focused on one section. And wow, just look at the result. This is a Manhattan plot, and it basically shows us all the genetic discoveries Emrigal made when it looked at 12 different heart readings, ECG leads, all at once. Every single one of those giant peaks shooting up past that red line, that's a potential new genetic discovery for heart health. By putting all the data together, it's finding stuff that was just impossible to see before.
Let's actually quantify this, because the numbers are pretty staggering. So Emrigal's confirmed 122 known genetic links, which is great, but it also found 20 totally new ones. And get this, it found 30 genetic markers that were completely invisible when scientists looked at each data stream on its own. That's not just a little better, that's a whole new level of discovery.
So, what's the big deal? Why does this all matter? Well, because this kind of deep genetic insight leads directly to better medicine. This new knowledge was used to build a way more